In any robotic system, we want our agents to go where we tell them to. This is especially pertinent for drone swarms, so we don't get collisions in midair. To do this, we need three things: accurate frame transformations, feedback control, and state estimation. On the right, you'll see my frame debugging panel. We need every measurement to be in the laboratory frame, which is different to the OptiTrack frame, the Tello IMU frame, the Tello body frame, and the Tello marker frame. I'll include a diagram and explanation on the GitHub, but trust me, if you can avoid it, you don't want to get involved in this kind of stuff. Once we're in the lab frame, which includes finding the transform from the drone to the lab, which is different every time we restart the drone, we have a Kalman filter that runs at 50 Hz. This fuses all of our sensor data and estimates the position, velocity, and yaw of the drone. OptiTrack by itself has sub-centimeter accuracy, so the purpose of the filter is actually to improve robustness and not precision. Sometimes if a marker is occluded, OptiTrack will drop out, and then we won't know what's happening, and obviously we can't tell where the drone is outside of the OptiTrack area in the lab. On the other hand, the Tello drone does all kinds of weird processing on board, uses strange conventions, and only broadcasts at 10 Hz, so it's very difficult to control the drone with only the IMU. So, without jumping into the maths, the filter allows us to get the best of both those data sources. If you don't have an optical tracking system, something as simple as a QR code with a known position can be used to stop drift and localize the drone into a global coordinate frame. So, we've seen how the Kalman filter estimates yaw. This allows us to project our velocities, which are measured along arbitrarily defined axes, into a fixed lab frame, and these velocities allow us to continue to estimate our position even when we don't have OptiTrack position data. You can see here, as I move in the Y and then X direction that we've defined in the lab frame, all of the messy data from the frame debugging panels resolves to nice smooth position estimates coming out of the Kalman filter on the left. It doesn't matter which way we're facing, we know the yaw of the drone and the frame transformations, so any measurements will be expressed in a fixed frame relative to the lab. If I fly the drone outside of the OptiTrack area, you'll see we still have a good position estimate. You can't see the drone on camera, but you'll have to take my word for it that it's fairly accurate. If I fly the drone back in, we'll pick up the OptiTrack measurement and then factor that back into our Kalman filter prediction. You can see for Y and Z, we were basically perfect after flying around. X was a little bit off, but our estimate is still directionally correct, and that is much more useful than having no data at all, while OptiTrack isn't giving us any information. Now we know where the drone is in space, but why is that useful? We can take where the drone is, and where we would like it to be, and use the difference between those two values to control the drone. This will allow us to ensure the drone's position is where we would actually like it to be. Because the Tello's onboard control scheme is a black box that we can't replace, we'll surround it with an outer proportional derivative control loop instead of having a kinematic space controller. The P proportional term yanks the drone towards the target, while the D derivative term will soak up velocity so it brakes as it approaches. We can live tune both of those on the panel on the right, and we have separate gains for X, Y, Z, and yaw. We can use the panel to set a target, allowing us to observe the system's responses to any of those three areas or all of them at once. We can also set the target to the current position to make the drone hover in place. So overall, these modules give us the infrastructure to know where the drone is, tell it where to go, and to fine-tune all of these processes to make sure they're as accurate as possible.